Today we shall discuss refraction through a parallel sided slab. It is an application for refraction of light at a plane interface. So we are going to discuss refraction through a parallel sided slab. Refraction through a parallel sided slab. So light is going to pass through a parallel sided slab, and we shall see different what actually happens in that case. Suppose this is that parallel sided slab you are having. Material of refractive index An surrounded by air. Here also air. It is having a thickness A T. So you have a slab, say glass slab, is having a thickness T and refractive index N surrounded by air. At one interface, you have a ray of light incident like this at an angle say I. I is the angle of incidence at the first interface where it undergoes refraction. Here it is entering from air to a denser medium, so it has to bend towards the normal. So instead of going like this, it will bend towards the normal somewhat like this. So it was expected to move like this. This is what it was expected to move, but it is bending towards the normal because it is entering from a lighter to a denser medium. Now it comes to the next interface, second interface. There it again undergo refraction. This time it is going from a denser to a rarer medium, so it has to bend away from the normal. So bending away from the normal, suppose is like this. I have taken I as the angle of incidence, then this is the angle of refraction at the first interface. If that is R, angle of incidence at the second interface will also be R. If that is R, this is I, this is R, this is R, this will also be R, and this is the angle at which the ray emerges. So I am going to call E as the angle of emergence. I have I angle of incidence, E angle of emergence. Now we shall see the relation connecting I and E. For that we will apply Snell's law at the two interfaces. Using Snell's law for the first refraction, Snell's law for first refraction. It is coming from air going into another medium, so I can write refractive index of air 1 into sine of angle there, sine I, equal to refractive index of the medium where it enters, n into sine of angle there, sine r. This is Snell's law. 1 into sine I equals n into sine r, which I put as equation. Okay, I will write that. 1 into sine I equals n into sine r. I will put as equation number 1. Now I will apply Snell's law for the second refraction there. Snell's law for second refraction. For second refraction, angle of incidence is R, angle of refraction is E. Snell's law, when I apply n into sine R equal to, goes to air 1 into sine of angle there E, which I put as equation number 2. Before that, 1 into sine E, I write sine E. But n into sine R equal to sine E, that is equation number 2. When I compare 1 and 2, I see here n into sine R in the RHS, here n into sine R in the LHS, so I can equate these two. From 1 and 2, sine E turns out to be equal to sine I. That will happen only when E equal to I. So what I am getting is angle of emergence is equal to angle of incidence. So angle of emergence is equal to angle of incidence. If angle of emergence and angle of incidence are equal, definitely the emerging ray should be parallel to the incident ray, then only that angle are equal. So this implies that the emergent ray is parallel to the incident ray. That is why I have shown parallel to the other. The emergent ray is parallel to incident ray. So what we see is, very important condition is that here it enters from air, goes to air. So both sides same medium, then only this relation is valid. So it is seen that when a ray passes through a parallel sided slab surrounded by the same medium on both sides, the ray passes emerges parallel to the incident ray, or angle of incidence is equal to angle of emergence. Remember, condition valid only when both sides same medium.